Dr. Lannes, could you start, please?
Yes. So thank you very much for this invitation. And so I will talk about vorticity and shallow water flows. So it's not very recent works. About 3 years ago I did this. But since your Professor Murashi asked me to deal with this topic, so I will present you these works. And so I will first remind you how you model this kind of flows in the irrotational setting, and then I will explain what are the differences when you take into account vorticity. So if we start from the water waves equation, so you all know the equation, so I will do it quite quickly. So just this is for the notations. Zeta is the free surface. I have a finite bottom. And so I have the Euler equations that you all know, dtu plus u grad u is equal to -1 over rho grad p and the gravity. So in the fluid domain, we have incompressibility. And in this first part of the talk, I will assume irrotationality also for the velocity field. Then you have impermeability of the bottom. And similarly, for the surface, it's the same condition, but the surface moves. So you have this kinematic boundary condition that dt zeta, the time derivative of the surface parametrization, is related to the normal component of the velocity at the surface. And then you have a boundary condition on the, yes?
Are you showing something? I'm only seeing your title slide.
Okay. Okay, we'll do it again. Okay, is it okay now?
That's better. Yeah, thanks.
Okay, thank you very much, David. And so, okay, so these are the equation of that you all know. So you have a boundary condition on the pressure also. So this is a set of free surface Euler equations. And when you want to do water waves, what you use the fact that you are in irrotational to use a velocity potential. So u is the gradient in x and z of a velocity potential phi. And then instead of working with Euler equation, you work with Bernoulli equation, which is the equation satisfied by this potential. So you just replace the divergence of u by saying that this is equivalent to say that phi is harmonic in the free domain. And Euler equation is replaced by the Bernoulli equation, dt phi plus 1/2 of grad phi square plus the potential of gravity is equal to the pressure. Okay, and we replace u by grad phi everywhere. So this is a set of free surface Bernoulli equations. And then the next set to reduce the equations is to remark that you have one unknown, which is zeta, which is on a fixed domain, which is the horizontal plane RD. But the problem with the velocity potential is that it is defined on a three-dimensional domain, the fluid domain, which is moving and which is unknown. So the basic remark is that actually you can rewrite the equations in terms of zeta and in terms of another function psi, which is also defined only on the horizontal plane. So the trick to do this, it was remarked by Zakharov more than 50 years ago, is to say that if you define psi as a trace of the velocity potential at the surface, so as z is equal to zeta, then you can remark that you can fully solve the velocity potential, since you know that it is a harmonic function in the free domain, that by definition its trace at the surface is psi, and that's by the impermeability condition, the normal derivative is 0 at the bottom. So there is a unique solution to this equation. And so it's enough to know this function psi. And so you can reduce the set of equations to actually two sets of functions, zeta and psi, which are defined on the horizontal planes, which are, of course, fixed. So what are these equations? So these equations are what are called the Zakharov-Craig-Sulem equations. So if you want to write this explicitly in terms of zeta and psi, so start with the first one, the kinematic condition. So you remember that it was dt zeta minus the square root of this and the normal component of the velocity, which is the same as the normal derivative of the velocity potential. And then if you want to be, you just introduce a notation, which is the Dirichlet-Neumann operator, which to every fluid domain determined by the surface zeta and the bottom b associates to function psi. You solve the velocity potential with boundary condition psi at the surface, and then you associate this normal derivative of the velocity potential. Okay, so this is a well-defined mapping, and this quantity you just denote it G of psi. Okay, so this is a Dirichlet-Neumann operator associated to the domain. And so the first equation can be written simply in terms of zeta and psi by using this Dirichlet-Neumann operator. So dt zeta minus G of zeta b of psi is equal to 0. So then you have to write Bernoulli equations in terms of psi. So I remind you that the Bernoulli equation was given by this. So this is in the whole fluid domain, but you also have a boundary condition on the pressure that at the surface P is equal to the atmospheric pressure. So if you take the trace of the Bernoulli equation at the surface, so this pressure term will disappear, and you will obtain that the trace of all these quantities is equal to 0. So this is a trace of the Bernoulli equation at the surface. You get rid of the pressure term, and then by using the chain rule, you can express all the derivatives of phi in terms of grad psi, which is essentially the tangential component of the velocity, and the normal derivative of phi, which is related to the Dirichlet-Neumann operator. So you have some computations. It's not important here. What is important is that by taking the trace of the velocity, the Bernoulli equation at the surface, you obtain the time evolution equation for this quantity psi. And this set of two equations are what is called the Zakharov-Craig-Sulem formulation of the equation. You have reduced the problem to a set of evolution equation on two scalar quantities zeta and psi, defined on the horizontal plane RD, which is no longer a free boundary problem. Okay, so this is a convenient set of equations. So this system has been studied a lot, and actually it contains all the information you need for the water waves problem. And in particular, if you know this zeta MC, you are able to find models that in terms of zeta and what I call V bar, which is an interesting quantity. This is the vertical average of the horizontal velocity. So you integrate the horizontal velocity from the bottom to the top, and you divide it by the water height. Okay, and so this is the vertically average horizontal velocity. And so the question is, so this is a physically relevant quantity, which is related to the horizontal discharge. And how do you get an asymptotic model in terms of these two quantities, zeta and V bar, from this Zakharov-Craig-Sulem system? So the way you have to do this is using some kind of asymptotic analysis. So you can rewrite the Zakharov-Craig-Sulem equation. I just take the gradient of this expression. So, okay, you have the red term grad psi. And what you want to do is that you want to express the blue term, so the Dirichlet-Neumann operator, and the red term grad psi in terms of zeta and this velocity V bar. Okay, so if we start with the blue term, with the Dirichlet-Neumann operator, actually this is very easy because we have an exact expression. The Dirichlet-Neumann operator applied to psi is equal to minus the divergence of h V bar. So this is quite easy to see, and this tells you that the first equation is equivalent to this, which is an exact equation, and this is what you obtain if you integrate the incompressibility condition. Okay, so this equation is actually conservation of mass. So it's a very natural equation. It is exact, and it is very simple. So this is why in physics, people usually like to write models in terms of this quantity, because this first equation is very, very nice. For the red quantity, the things are not as simple because you cannot have an exact algebraic expression of grad psi, which, as I said, is essentially the horizontal, the tangential component of the velocity at the surface. We don't have an expression of this in terms of this average velocity V bar. So what you have to do is to derive an approximate expression. And if you want to have an approximate expression, you need some small parameter, and so you need to define some asymptotic regimes. Okay, and one possible regime, this is not the only one, is the regime of shallow water. And in this regime of shallow water, we are going to be able to derive such models. So what is a shallow water model? So it's, you have to define some quantities. So here are the three quantities that you have to define. You have typically one horizontal scale, which I denote L, which is typically, for instance, if you have a swell in the ocean, this will be the wavelength of the swell. If you have a tsunami, it will be the length of the tsunami, etc. A second scale is the depth, of course, H0. And a third length is the amplitude of the waves you're looking at. Okay, so you have three lengths, and with these three lengths, you are able to define two dimensionless parameters. So one is a ratio of the amplitude of the waves over the depth. So this is called the amplitude parameter. And from a mathematical point of view, it will describe the nonlinear effects in the equations. And you have this parameter mu, which is the ratio of the depth over the horizontal scale squared. So this is called shallow water. So you are in shallow water if the depth of the water is much smaller than the horizontal scale. Okay. And so the regime that we are going to consider is a regime where mu is small. Okay, and we are going to do our asymptotics with respect to this small parameter mu. So first you rewrite the equation in dimensionless version. So you rescale the equations. And so now this is why you have these parameters in front of the equations. And now in this rescaled equation, the depth is at rest is 1 and the surface of the water is epsilon zeta. So the vertically averaged horizontal velocity is defined like this. So it's 1 over h times the integral from the bottom to the top of the horizontal velocity v. And the shallow water asymptotics. So you assume that mu is small. And you want to find an asymptotic description relating gradient of c, this red quantity, in terms of zeta and v bar. So how do you do this? What you are going to do, you see that if you are able to find in this integral an asymptotic description of the velocity field in terms of mu, then you will deduce an asymptotic description for v bar. And in order to have an asymptotic expansion of v, it is enough to have an asymptotic description of the velocity potential because v is equal to gradient of phi. So we are going to look at an expansion of the velocity potential in terms of phi0 plus mu phi1, etc., etc. You plug this into the equations and you solve it. So I will not do it here. This is quite classical. But what you find using this, and this is the what I want to insist on is that you get a relation by finding you are able to find the structure of the vertical dependence of the velocity field in the fluid domain. And thanks to this, you are able to find a relation between grad psi and v bar. So at first order in mu, they are the same. This is what physicists call the columnar motion, that the velocity, the horizontal velocity at first order does not depend on the vertical variable. And so the horizontal velocity at the surface is the same as the average horizontal velocity. And then at first order, so if you neglect the terms of order mu in your full equations, in these equations, you can replace grad psi by v bar and neglect all the terms of order mu like these ones. And you find the Saint-Venant, or in English, nonlinear shallow water equations, which are this equation, which is a set of hyperbolic equations. Okay, so this is the derivation of this asymptotic model from the Zakharov-Craig-Scullem equations. And of course, you can define more precise models by going further into the asymptotics. So if you keep the terms of order mu and you just neglect the term of order mu square, then you have a next order approximation that actually it's okay. It's grad psi is equal to v bar plus t of v bar. I forgot the t of v bar here, which is a second order operator. And then when you replace this in the in the equation, you find a perturbation of the nonlinear shallow water equation by green terms, and these green terms, they are due to this higher order dependence of the velocity field in terms of the vertical variables. And these red terms, they are of dispersive nature. You see that this t here, essentially it's minus Laplacian. And so you see that this is a dispersive term. So essentially, if you know the BBM equation, this is the dx squared dt term in the BBM equation. Okay, so you have the basic model is a nonlinear shallow water equation. And if you go further in the asymptotic expansion of the velocity field, you obtain the red term, the green term, which are dispersive terms. So these dispersive terms, these green terms, they come from the fact that if you go to the next order, the dependence of the velocity field is no longer independent of the vertical variable z, but it has a dependence on this variable. So it really is a consequence of the vertical variations of the horizontal velocity. Okay, so this is what is important to have in mind. So for this kind of model, there have been plenty of works to derive and justify this model. So they starting from probably Friedrichs, then Kanonishige, Craig, then with Boris Alvarez and also Iguchi independently, we have justified these Green-Nagdi models. And more recently, Iguchi has studied a family of models, which is called the Isobe-Kakinuma models, which you can see as further improvements of these Green-Nagdi equations. Okay, so the idea behind this is the same. Okay, so this is the framework when you are irrotational, and with this model you can do some numerics. So this is, for instance, a tsunami arriving on an Iceland. So we have good comparisons with experimental data. And what you can see from these numerical computation is that you have, on the one hand, you have wave breaking, which is something mathematically that is quite open to understand. And you also have generation of vorticity, that you can see some small vortices here. So which means that when you approach the coast, you should be able to handle these vorticity effects. So how can we change what we have done in the previous analysis to include vorticity? So these are some photographs taken by a collaborator who is a physicist in Bordeaux and who is, among other things, is studying rip currents, which are vorticity currents created by wave breaking when they reach the shore. Okay, you can see them in these photographs. So the motivation was to be able to handle such vorticity effects. So going back to my previous approach, I start from the Euler equation, exactly the same equations, except that I remove this irrotationality condition. So what can we do to handle this more complicated case? So in the irrotational case, we had really used this irrotationality equation because we had said that u was the gradient of a velocity potential. Okay, and then we used the Bernoulli equations, and we got rid of the pressure by taking the trace of the Bernoulli equation at the surface. Of course, in the rotational case, we cannot do this anymore, because we cannot say that curl u is that u is a gradient of phi. Okay, and then it was also convenient to work with this Bernoulli equation because by taking the trace of this equation at the surface, we could derive reduce the problem to a system of equation on zeta and on psi, which was a scalar function defined on the horizontal plane. So this was the Zakharov-Craig-Sulem formulation. So now in the rotational case, curl of u is some quantity omega, which is not zero. What we know about this omega is that it solves the vorticity equation. So dt omega plus u grad omega is equal to omega grad u. Okay, but it's not zero. It's not. We don't assume it is constant, so that we cannot work with the Bernoulli equation. And the first thing is, how can we use the boundary condition on the pressure P? In the Bernoulli equation, we took the trace of the Bernoulli equation at the surface, and this was used to get rid of the pressure term P. So now, how can we exploit the fact that at the surface P is equal to the atmospheric pressure? So what we can do is that we can take the Euler equation, which is this one, and remark that the gradient of P at the surface actually is proportional to a normal vector. Why? Because P is constant at the surface. So it means that the tangential derivative of P is equal to 0. Okay, so there is only a normal component. And so it's n proportional to dz of P. And n is this non-unit normal vector. And therefore, at the surface, we know that this quantity will be a normal quantity. So if we take the trace of this Euler equation at the surface, and if we take its tangential components, then this will make this pressure term disappear. Okay, so what we can do is to take the vectorial product of the resulting equation with this non-unit vector n, which is equivalent to looking at the tangential component. So if we do this, we are going to obtain an equation on the tangential part of the velocity at the surface. Okay, and so if I use this notation that I use with a bar, the trace of the velocity field at the surface, and v is the horizontal component and w the vertical component, I will define this u tangent or u parallel here as the horizontal components of the velocity field plus w grad zeta. Actually, this, if you take the cross product of the velocity field with n at the surface, you find that it is of this form. So you see that it's essentially the horizontal component of this quantity. So it's essentially the horizontal component of the tangential velocity field at the surface. Okay, and you see that you can deduce the vertical component because, as we have seen, this this is there is a constraint at the surface because the pressure is constant. Okay, so we are going to derive an equation on this quantity. So this is what we do. We take Euler equation, take the trace at the surface, take the cross product with n to eliminate the pressure term, and after some computation, what you obtain is an equation on this quantity u parallel. So this is a vector in R2, okay, plus g grad zeta, so horizontal gradient of zeta, plus 1/2 of grad of u parallel square, plus some other terms. And as a source term, you have a term which is related to the normal component of the vorticity evaluated at the surface. Okay. And then, so this way of proceeding, what is it equivalent to if we do it in the irrotational case? Okay, this should work also in the irrotational case. And actually, if you look at what happens in the irrotational case, you remark that u parallel is exactly the gradient of psi. Okay, and this quantity omega dot n is equal to 0, so that in this case we obtain an equation which is exactly the equation we had obtained on psi. I mean, with the gradient of the equation we had obtained on psi in the Zakharov-Krejculem formulation. And how do we generalize this to the rotational case? We are going to say that u parallel. So in the rotational case, this is no longer a gradient vector field, but we know that since u parallel is a vector field in R2. We can decompose it into a gradient vector field plus an orthogonal gradient vector field, and I will call this quantity psi tilde. Okay, so this is the way I will define this scalar quantity psi. Psi is defined as by the fact that grad psi is the gradient component of u parallel, and u parallel is essentially the horizontal component of the tangential velocity at the surface. Okay. And so I want to obtain an equation on psi. So we have this equation on u parallel, and I decompose u parallel into grad psi and grad orthogonal of psi tilde. So the first thing that we get is that by projecting this equation onto the gradient vector field, what we obtain is that we have this equation on psi, which is a generalization of the equation of the Zakharov-Krejculem equation in the irrotational case. So dt psi plus g zeta plus 1/2 of u parallel square. So in the Zakharov-Krejculem equation, this was grad psi plus some other nonlinear terms, which are of no importance here, is equal to minus this Fourier multiplier applied to omega dot n times v perpendicular. Okay, and so we have obtained a generalization of the Zakharov-Krejculem equations. So this generalization is the following one. The Zakharov-Krejculem equation was dt minus un was equal to 0, and then this equation for psi, which was the trace of the velocity potential at the surface, and omega was equal to 0. And we had seen that q dot n could be expressed in terms of the Dirichlet-Neumann operator. And so this set of equation was a closed system of equation in zeta and psi. And this we had used then to derive asymptotic models, etc., etc. So now that we are in the rotational case, we still have this equation, it is zeta minus u dot n is equal to 0. We have obtained an equation on psi, but psi now, I remind you that it is defined as grad psi is the projection of the horizontal component of the tangential velocity onto a gradient vector fields. Okay, so you obtain this equation, which is a generalization of this one, especially in particular, you have this green term here. And of course, omega is not 0, you have omega, which is given by the vorticity equation that we have seen before. And what you can prove, and this is something we did with Angel Castro a few years ago, is that this is also a closed system of equation in zeta psi omega. Meaning that if you know zeta, if you know psi, and if you know the vorticity omega, you are able to rebuild all the velocity field in the free domain. And in particular, you are able to compute the normal component of the velocity at the surface, the tangential component of the velocity at the surface, and also the horizontal vector field at the surface. Okay. And this system of equation also is well posed, and we have done this in this paper. So we have a generalization of the Zakharov-Craig-Sulam equation. But there is something which is, okay, I will go back, excuse me. There's something which is a bit annoying in this generalization, is that in the standard Zakharov-Craig-Sulam equation, the interesting fact was that this was reduced to a set of equations of two quantities zeta and psi that were cast on the horizontal plane RD. Okay, so we had started from a d+1 dimensional problem. So d is the horizontal dimension, and reduced it to a d-dimensional domain. In this case, we still have zeta and psi defined on the horizontal plane RD, but omega is an evolution equation which is defined on the full dimensional d+1 dimensional fluid domain. Okay, so we lose this dimension reduction. So maybe omega can be constant, for instance, in some cases. So in this case, this equation disappears, but otherwise we have a dynamic which is more complicated, and we cannot reduce the dynamic of the vorticity to an equation, a d-dimensional equation. The dynamics of the vorticity, if it is not trivial, like with a constant vorticity, is really a dynamic which is d+1 dimensional. Okay, so this will be a problem if we want to obtain asymptotic models in shallow water models. The question is, do these shallow water models with vorticity require to work in a d+1 dimensional domain, or can we still work with d-dimensional domain as in the irrotational setting? Okay, so this is the question that is unclear. So in order to proceed to these asymptotics, we have to work with dimensionless version of this generalized Zakharov-Craig-Sulam equation. And we are going to define some quantity R. And this quantity R is what I will call the Reynolds tensor. In this, why is it called the Reynolds tensor? Because I am integrating in the quadratic term, which is the integral from the bottom to the top of v square. V is the horizontal component of the velocity. And if, as in the irrotational case, at first order, we have seen that the horizontal velocity field does not depend on the vertical variable z. So in this case, the integral of v square is h times v bar square. Okay. But if we have a dependence on the z variable, you have a reminder term, which is this. Okay, the difference from v with respect to its vertical average to the square. Okay, so in general, this quantity is not zero. In the case of in the irrotational case, this quantity turns out to be neglected because each of these terms is of size mu. So this is of size mu square, so you can neglect it at the precision of the model. But when you put vorticity, the problem with vorticity is that you have a shear which is created by the vorticity. So you have a vertical dependence of the horizontal velocity created by the vorticity. And so an effect of the vorticity is that this term is not negligible anymore. So in order to see it, I will write the equation under another form. So this is what I say here. So V minus V bar. In the irrotational case, we have the only dependence of the horizontal velocity field in the vertical variable was due to non-hydrostatic effects, and they were quite small. So this is why in the quadratic terms they disappeared. But now we have the non-hydrostatic effects, like in the rotational case. But in addition to this, we have a vorticity-induced shear. Okay, so we have to understand the effect of this vorticity-induced shear velocity. So a way to understand what happens is to rewrite the Euler equation under this form. So we have already seen that the first equation, the kinematic equation, can be written exactly in terms of zeta and the vertically average horizontal velocity v bar. So dt zeta plus divergence of h v bar. So h v bar is the discharge. As I said, this can be obtained by integrating vertically the incompressibility condition. You do not need to use the irrotationality condition to obtain this equation. So this equation remains exact. And then if you want to obtain an equation on V bar, a natural way to do it is to integrate vertically the horizontal component of Euler equation. Okay, so if you integrate the equation, the horizontal component of Euler equation, which is dtv plus u grad v, etc., then you find dt of hv bar plus divergence of hv bar square plus this term r here. And you see that this term r here is really comes from the divergence of the integral of v square, and I decompose v as v bar plus v minus v bar. So this is why I can write it like this. And you have also the integration of the gradient of the pressure. So if you want to look at what happens, if you look at the level of the Saint-Venant equation, where you want to have a model which is precise at order mu, so you neglect all the terms of order mu. So in this case, you don't have much influence of the vorticity terms, because this, what I call Reynolds tensor R, is of order 1, and it has a small parameter mu in front. So you can neglect this term if you neglect all the terms of order mu. Okay, so you drop this term, and for the integral of the gradient of the pressure, you can find that the pressure actually at first order is hydrostatic. So it is just the pressure created by gravity plus terms of order mu. So you drop them. And if you do this, then you obtain, then you obtain the standard shallow water or Saint-Venant equation. But then if you want to work at a higher order model, the level of the Grenadier model with the dispersive term, then what happens? Then, of course, in this pressure, you will have to include the order mu term. So you have the dispersive effects, which was my operator T before. So this is not a big problem. But you have also another problem, which is much bigger, which is that you need to understand this Reynolds tensor R. You cannot drop it anymore. You cannot neglect it anymore. And in particular, this operator R, this is the integral in the vertical integral of V minus V bar. So you need to know the velocity field in the whole fluid domain. Okay, so this quantity requires the computing of quantities that are d+1 dimensional. So the question is, do we still have to work with d+1 dimensional equations to compute this Reynolds tensor R, or is it possible to avoid this computation of three-dimensional equation? So the idea is actually inspired by what is done for the study of turbulence for isentropic Euler equation in compressible gases, where the idea is that, and this is why I call this tensor Reynolds tensor. The idea is that you are not going to compute R explicitly. The idea is that you are going to look for equations on this tensor R. So, and you will write a set of equations and you will find a cascade of equations. I will show it in the next slide. And at some point of this cascade of equation, you need an argument to end the cascade of equation. Okay, so for gases, this is what is called a turbulent closure. So you have to find something that closes the cascade of equation. And I will show you that here we can find a natural condition to close this cascade of equation. So this is what I am going to do right now to explain to you how you can derive, extend the Grignard equation in the presence of vortices. So let me start with the model that you obtain, as I said. So you start at first order approximation when you say that the pressure is hydrostatic. So it gives you this dx zeta here. So this is the nonlinear shallow water equation. I do it in dimension 1, but we did it, of course, in the two-dimensional case. So you have the hyperbolic nonlinear shallow water equation. As in the irrotational framework, if you include the non-hydrostatic terms in the pressure equation, you have dispersive terms that appear. Okay, so these equations are, as in the irrotational case, you have this operator mu t that appears in front of this here. So essentially t is like a dx square, so minus dx square. And these are additional nonlinear terms. So this is like in the rotational framework. The new things comes from the Reynolds tensor. So the Reynolds tensor, I remind you that it's related to the integral of the square of v minus v bar, where v bar is the average of v. And I told you that there are two reasons that can make v be different from its average v bar. One is due to the non-hydrostatic terms, the dispersive terms, if you prefer, of the velocity field. Okay, so this induces a vertical dependence that is at next order, but that is here. And the other reason is that you can have a shear velocity which is created by the vorticity. So since you have a quadratic terms and that each component v minus v bar contains one component, one variation from the average which is due to the non-hydrostatic term and another one which is due to the rotational term, then in this quadratic term you will have one which is the rotational term against the non-hydrostatic term, another one which is the quadratic self-interaction of the rotational term, of the shear velocity induced term. And you would also have a quadratic term, non-hydrostatic, but as we have seen in the rotational framework, this term is of size mu square, so you can drop it, because I remind you that the Grignard equation are at precision mu square. So all the terms of your order mu square, you drop them. But a priori, you have these two terms. So if you do the computations, which are a bit complicated, then you find that you expect some interaction between the average velocity v bar and the shear induced by the vorticity. And so what is the shear induced by the vorticity? If you define the shear induced by the vorticity is exactly the integral of omega, of course, vertical integral of omega. And the star means that I take it of a zero vertical average. Okay, so I take it like this. And this quantity V sharp actually is the second moment of this shear velocity. Okay, so you find an operator, which is a differential operator, which is quite simple, but I don't write it, between V bar, which is here, and V sharp. The problem is we don't know V sharp. If for V sharp, we have to compute the shear velocity, and in order to compute the shear velocity, we have to compute omega, then we have to solve the equation for omega, which is d plus 1 dimensional, and you don't want to do that. You don't want to lose 1 dimension. So you want to derive an equation for V sharp. And actually, you have one. You can try to time differentiate it and look what happens. And you find that you have an equation for V sharp, which is quite simple. It's essentially a transport term of the velocity V bar on V sharp over H. Okay, so you are able to handle this interaction of the non-hydrostatic terms with the shear induced by the vorticity. So now what about the quadratic self-interaction of the shear velocity? So this quantity is can be written like this: 1 over h dx e, where e is the integral of the square of this shear velocity. So it's the same. We don't want to compute this shear velocity, and we don't want to compute omega. So we look for an equation on E. And this is where we will find our cascade of equations. We find an equation on E, which is a transport equation on E over H3. But you have coupling with another tensor, a higher order tensor, which is F, which is now the third order tensor. And it's the same. You are going to look for an equation on F. And this equation on F will imply a fourth order tensor, and you will have this cascade of equation. And you have to close this cascade of equation. And actually, it's very easy to close, because what you can show is that at each order of the cascade, the contribution is smaller. So the closure, if you want, you can call it the turbulent closure of the equation, is to say, I will close my cascade when the contribution will be of size mu square or smaller, because this is the precision of the Green-Nagdi equation. So in the end, you stop it here. So you have an extended set of Green-Nagdi equation. So you have more equations, but what is nice is that they are still one-dimensional in this case, and not two-dimensional. You don't have to solve the equation for omega. Okay, so this is how you can describe the presence of the vorticity. And in the case of constant vorticity, what is nice is that all these new equations, they degenerate to the mass equation. They're equivalent. So there is no additional equation. And so this is something that Professor Murashige knows very well, because he has looked at this with Choi. And you have, in this case, a system of two equations only, because in this case, all these additional equations degenerate into this mass conservation equation. But in the case where omega is not constant, you have an extended set of variables. So I will go fast now. You have you can analyze this model. You have local conservation of energy. You can study the influence of vorticity on the solitary waves. You have some change of shape. If you have positive or negative vorticity, you can prove that you have extreme, in some cases, extreme size for the solitary wave with an angle at the summit. This angle is quite. The solution is quite stable, because we could observe it numerically with Fabien. And okay, so just to end this, so this is a computation. So then after, you can reconstruct the vorticity in the free domain just using transport equation. So it's quite simple to do it. So this is fun just by using one-dimensional equation and not two-dimensional equation, in spite of the fact that you have a two-dimensional dynamic inside. Of course, there are many things to understand. One of it is the generation of vorticity by wave breaking. So you have interesting works by Gavrilyuk and Richard on these topics. So I will stop here. So I have recently made a review in nonlinearity where I comment all these aspects. So if you're interested, you can look. And I will stop here, because I think my time is over. So thank you for your attention.
Thank you very much. Thank you very much, Dr. Lannes, for a very interesting talk. Okay, now let's open questions and comments from audiences. Any questions or comments? Yes, please.
If I may, I have two questions. I guess first, let me start with the model you developed here at the end. I don't have to tell you that for model equations like this, there's long history of validation theorems for the models, right? You know, this is largely the content of your book. Using a closure like this, is there any hope of proving a validation theorem for this model?
Yes, I did not mention it, but in the paper, so for the earlier equation with vorticity, with this new formulation with Angel Castro, what we did is that we proved the bounds, uniform bounds in shallow water for the, and so and then we in another paper in the GFM we derived these asymptotic models. So all the approximation we did in this approximate model are justified. Okay, so if you want to justify the models, the only thing you need to do is to look at the well-poserness of these asymptotic models and to have the energy estimate on it. So in particular, if you do it at for the shallow water case, then it's the standard shallow water equation. So this is justified. For the extended Green-Nagdi equation, we did not do it, but I guess it could be done. But we didn't. But the main part is that the bounds you need for the solution of the earlier equation, this we did it. So I think it's there should be justified. But it's not. It's true that it's not done.
Okay, great. So my second question was about numerics you showed around, I think it was around slide 13.
13, yes. Okay. Oh, this one?
Yeah, so
oh, yeah.
Right. So this was before you got into the rotational models, right?
Yes.
You know, so those numerics there, are they using an irrotational?
Yes. So okay, what happens is that what you use the standard Green-Nagdi equation. Actually, normally you take initial data that are irrotational because this is how you derive them from the earlier equations. But you could also use them with the so it's vertical vorticity, so it will be the orthogonal gradient of V bar, and this you could use it for initial data which do not satisfy this curl-free condition, and in particular when you have boundaries, when you have wave breaking, then you create numerically solutions that do not satisfy this, and so you still your model still can use these quantities, but of course there's no reason why it should handle it physically correctly. Okay, right. You don't have a, so what we see here is that this appears, so it means that we should have a model that can handle this, even though this particular model handles it, but probably not correctly.
Right. Okay, great. Well, thanks a lot. It was a great talk.
Thank you.
Thank you very much. Any other questions? Yes, so may I ask you questions? It's for this case, it's even for this case, can we define the vertically averaged velocity? Is it, I guess it's near the shoreline.
Yeah, I mean, for in this case here, yes. At the limit, it corresponds to the velocity itself, because
itself. Oh, okay.
But then okay, it reminds me that I remember we discussed in Kyoto last time about this, and in the case of constant vorticity, and that you have different qualitative behavior in your models with Shoy, and I forgot to mention it. And the reason we find different things is that when you have a constant shear velocity, so what I say here in my case is that I take it, I say that I consider a V bar to be the average velocity. So it means that for me, this constant shear velocity has a zero vertical average. And in your case, you consider that I think the velocity is 0 at the surface.
That's right. That's right.
So it means that when you look at solitary waves, etc., if you want to make the link between your paper and mine, what you have to do is that you have to allow non-zero velocity at infinity. Because you see that if you have a shear velocity, then it's what do you say? It's you say that there is an average to this shear velocity. So you can say it's zero average, or you can say that what is the zero velocity is the velocity at the surface, and then it's not the same. Okay, so in this case, it's not clear what the condition at infinity is, and so if you play on this, then you can find, and there's no contradiction. So this is the good news.
Okay. Yes, you're right. Yes. It's a good news. Thank you very much. Okay. And about the rotational model, I have a question. It's, can we apply your theory to arbitrary value of vorticity?
Yes. What do you mean?
It's for shallow
water. The asymptotics, as I told David, is justified in shallow water. But in order to have this uniform bounds, I need some constraints of the size of the initial vorticity. So it has to be of size square root of mu or smaller, which means that if you see it, a rotation like this, the length of the radius of vorticity should be like the depth of the fluid. If you have a stronger vorticity, it means that, for instance, if you have boundary layers or something like that, then you don't have the uniform bounds for my solution. Okay, because in this case you have to use more refined technique like boundary layers, I guess, or something like that. But so our uniform bounds are in this regime of vorticity, which is square root of mu or smaller, and this is the framework in which we derive our asymptotic models. But of course, in the derivation of the asymptotic models, you could work with stronger vorticities.
Okay, thank you very much. It's a very nice talk. Any other questions or comments? Okay, thank you very much again, Dr. Lannes, for very nice talk. And thank you very much.
Thank you very much.